Hi, everyone. Welcome back to Dave's Math Channel. I'm your host, David Tear, and today I'm going to talk about how to do arithmetic in different bases. And at the bottom of this slide, you can see a couple examples of that. The problem on the bottom left is an example of addition in base 8, and the one on the right is an example of subtraction in base 4. I'll get to that later. But anyway, so first I want to talk about what we mean by different bases. Well, we all use base 10. That's also known as decimal. That's the number system we all use in most of the world. I think pretty much the whole world actually right now. It just means we use the digits 0 through 9. I'm sure you guys are all familiar with how we use numbers. And it's kind of the same idea on other bases. It's just an instead of we just have a different set of digits. So, for instance, binary, that's base 2. That's what computers use, by the way. All computer hardware, all computer arithmetic is done in binary. Computers only use two digits, 0 and 1, and the reason for that is because the way they work is they either have a current flowing through a particular part of the circuit that represents a particular bit or binary digit. In that case, it's a 1 if there's current flowing, and it's a 0 if there's not. So that's how computers work. And but that's a very simple system. There's only two digits, 0 and 1, and Octal. The other two number systems shown on this slide are also used with computer programming a lot because they're very closely related to base 2. Base 8, since 8 and 16 are both powers of 2, 8 is 2 cubed and 16 is 2 to the fourth power. It turns out, as you'll see later, that it's very easy to convert from binary to or from binary with octal or hexadecimal. But octal just uses the digits 0 through 7. You stop at 7, which is 8 minus 1. Hexadecimal, you actually have to add 6 new digits, A through F, after 9, because it requires 16 different digits. So A represents 10, B 11, C 12, D 13, E 14, and F 15. We stop at 15, which is 16 minus 1, but we need new symbols for those numbers because they have to have a single symbol. So anyway, those are the bases, some common bases, but you can do this for any base you want. And here's bases 3 through 9, and each of them have names. I think there's probably names for every base up to 20. But here's the names of bases 3 through 9. So base 3 is called ternary, and it uses 0, 1, and 2. Base 4 is called quaternary. The names of the bases are all based on the Latin names of the number in the base. So base 4 is quaternary, that uses 0 through 3. Base 5 is quinary, that uses 0 through 4. Base 6 is centary. I've hardly ever used these names, by the way. I think it's easier to say base B, where B is your base. But, they do have names. I guess people like names. So base 6 is called centary, 0 through 5. Base 7 is called septernary, 0 through 6. And base 9, I guess we already saw base 8, that was octal. Base 9 is called nonary, that's 0 through 8. Anyway, so now I just want to talk about, counting in these different bases. I'm going to go through all the arithmetic operations in kind of order of difficulty. So counting is the easiest thing you can do in any base. And we all know how to count in base 10. I mean, you learned that when you were a kid, probably before you even went to school. So we know how to count in base 10. We use the digits 0 through 9, but then by the time we get to 10, we write that as 1, 0. Yeah, because we don't have a symbol for 10. And then we keep going. We write 1, 1, 1, 2, 1, 3. And you do the same thing on all the other bases. It's just that instead of stopping at 10, as you did with base 10, you stop at your base. So these columns go through the bases in decreasing order. They start at base 12. Base 12 is also called duodecimal, by the way, and a lot of people really like base 12. I do too. There's even been a lot of proposals to switch to base 12, and I think there are a lot of people that prefer base 12 to base 10. I'll get into that later. But you're starting at base 12, so we have all the numbers written down 0 through 12 uh, in the rows, and then by the time we get to 12, we write that as 1 0. Notice that we've written 10 as A instead of 10 because now we have a new symbol for 10 at base 12. And then 11 we write as B. This is a very common custom. When we get past 9, we start using letters instead of numbers for the symbols. You can do this up to base 36, and it's people very seldom use a base as bigger than 36. Babylonians use base 60, but they use 2 symbols for their numbers. I'll get to that later. But anyway, yeah. So it's the same thing on all these other bases. I'm not going to go through all these other examples, but you can see for yourself, like base 11, 10 you still call A, but then by the time you get 11, you have to write that as 1 0, and then 12 you write as 1 1. You just keep counting the way we learn how to count in base 10. You do that in each base. I think I'll go through the last example, base 2, binary. This is the one with the fewest symbols, just 0 and 1. It's a pretty cumbersome base to work with because you have to, the numbers you write down are pretty long in base 2. That's a disadvantage of using a small base. The advantage is you have fewer symbols. The disadvantage is you have more of them. So look at what happens in base 2. 0 is 0. That's pretty obvious. 1 is 1. But you can't write 2 as 2 because there's no symbol for 2. So you write 1 0 instead. And then you continue like before. The next number after 1 0 is 1 1. But then, you can't write a 2. So you might think you have to write 2 0, but you can't do that either. So you actually have to add a third bit, third column already, just by the time you get to 4. 4 is 2 squared. So now you're writing 4 as 1 0 0. Let's keep going. 1 0 1. Just do the same thing we did before. There's no 2, so you have to write 1 1 0. And then you have to write 1 1 1 for 7. And then by the time you get to 8, you have to carry everything again. Once you get all ones, the next number you get in binary, you have to add a new digit and make all the other ones 0 again. It's like you do in decimal if you get all 9s. And so 8, you write as 1 0 0 0. Keep going. 1 0 0 1, 1 0 1 0, 1 0 1 1. 12 is 1 1 0 0. So I think you kind of get the idea how to count on these different bases. That's the easiest thing you can do on different bases. Now I want to talk about how to do arithmetic in different bases. And this is harder, but it's really not any harder than what we learned when we learned how to do it in decimal. I mean, let's look at these examples here. So I have 3 bases written down for doing addition in different bases. So base 10, you all know. You learned this probably in grade school, grade 2nd or 3rd grade. I'm sure you guys learned how to add numbers with more than one digit. You have to do a thing called carrying. I'll just go through this example just to remind you what you learned when you were in 2nd or 3rd grade. So if you wanted to add 978 plus 856, what do we do? We started at the rightmost column, 8 plus 6. That's 14. But 14 is bigger than 10, so you have to carry a 1. That's why we write this 1 in red above the next column. So now we're adding 1 plus 7 plus 5. That gives you 13. And again, you have to carry because 13 is bigger than 10. You write another 1, but you write down the 3. Keep going. 1 plus 9 is 10, plus 8 is 18. And you write down an 8, and you carry the last 1 and write a 1. That's how we all learn how to add. And you do the same thing on these other bases. Let's go for the example in base 5. So base 5, you're adding these pretty big numbers in base 5. How do we do it? Well, we do the same thing. Start at the right column. 4 plus 2. We all know that's 6. 6 is bigger than 5. We have to write 6 in base 5 as 1 1. So we write down the 1, but then we have to carry the next 1. So now you have 1 plus 1 plus 1. That's 3 in base 5, just like it is in base 10. 3 is smaller than 5, so we don't have to worry about it. And now you're not carrying anything. Now you have 2 plus 3. 2 plus 3 is 5, but 5 you write as 1 0 in base 5. So now you write down the 0 and you carry the 1. And now you have 1 plus 4 plus 3. That's 8, but we have to write that as 1 3. So we write down the 3. And then we carry the 1 again. 1 plus 2 plus 0. That's 3. We don't have to worry about that one. We're not carrying. The next column, 1 plus 4 is 5, which we write as 1, 0. So we write it as a 0, carry the 1, and then the last column is 1. Voila. 1, 0 is 3, 3, 0, 3, 1, and base 5 is your answer. And same in base 2. I'm not going to go through the example in base 2, but you can do it yourself. So the basic idea, I think the upshot, what I want you to get out of this is you're really doing the same thing you did in base 10. The only thing you have to remember is that your digits only go up to b minus 1 instead of 9 in these different bases. So that's how you do addition in these different bases. And subtraction. Subtraction is kind of the same idea, but subtraction is a little harder than addition. I'm going to go through this. I'm not going to go through the example on the left. That's addition. I already showed you how to add. But let's look at the example on the right. 2, 3, 2, 1 in base 4 minus 1, 3, 3, 2 in base 4. Let's go through this. So now what are we doing? We're doing 1 minus 2, but 2 is bigger than 1. So we have to borrow a 1. So we're really doing 1, 1 in base 4 minus 2 in base 4. That's 3. And so we write down the 3, but now we've borrowed. So we have to actually do 1 minus 3 or 1, 1 minus 3. That's going to give you a 2 for your next column. And we borrow it again. So now we're doing 1, 2 minus 3 in base 3. That's going to give you a 3. And again, we actually borrowed in each column. So now we're going to do 1 minus 1, that's 0, so we don't write down anything else. So that's how you subtract these numbers in base 4. Same as you did in base 10. You're just borrowing instead of carrying here. And then multiplication, same idea. And I don't know how many of you guys remembered shift and add multiplication. This is probably one of the hardest things you had to learn in grade school when you were learning arithmetic. And I don't even know if all kids learn this anymore. But it is something I think every kid should learn. I had to learn it when I was in school, and all the kids I knew had to learn it. I think a lot of kids have forgotten how to do this because of calculators. I don't want to get into that, but I think that we've forgotten how to do a lot of basic arithmetic thanks to the calculators, and I'm not going to go into that. That could be a whole nother lecture, but let's just remember how we learned how to do shift and add multiplication. So we do the same thing in base 5 as we learn how to do in base 10. So I'm not going through every step, but you know what to do. You multiply 343 times 4. You just use the last digit of the second number. So if you multiply 343 in base 5 by 4 in base 5, I'm not going to go through all the steps. You get 3032 in base 5. That's the first number you write down. And then you do the same thing. You multiply 343 in base 5 by 20 in base 5. You don't really have to worry about the 0. You can just shift it to the left. So 343 times 2 will give you 1241, but then you have to add a 0. So your second number you're adding is 124 is 10 in base 5. I already showed you how to add in base 5. If you do this addition, the final answer you get is the thing on the bottom, 20442 in base 5. Voila. Shift and add. Still works on other bases. And the last thing, probably the hardest thing you had to learn how to do when you were learning arithmetic was long division. I think most kids don't learn that until 4th grade, if they learn it at all. I mean, we had to learn it in 4th grade. But it's the same idea. I'm not going to go through all the steps here, but the only point I'm trying to make, I think you guys get the idea, that arithmetic in these different bases is exactly the same as arithmetic in decimal in base 10. You're just doing everything with a different base where, you're remembering to write 1, 0 as B, where B is your base. And so, these are examples of long division. The top example is you're dividing 2155 in base 8 by 61 in base 8. Here they spell out. This is another convention, by the way. Some people like to spell out the name of the base instead of writing the number symbol for it. I prefer writing the number symbol for it. But so if you did all the long division, which they show here on top, at the top middle, you'll find that the answer is 27, that's your quotient in base 8, plus the remainder of 6 in base 8. Same way we did in a decimal. You can check this for yourself. But the example on the bottom, same thing. You can do this in any base. Here they do it in binary. So if you're dividing 1 0 0 1 0 1 1 in base 2 by 1 1 1 in base 2, if you do the long division, you'll find that you get your quotient is 1 0 1 0 with a remainder of 1 0 1. And they even check these things. I mean, they're doing the shift and add multiplication in the right, which I just showed you how to do. So you can check in the same way. So just remember this. I think this is the key to remember how to do all arithmetic at any base. Same rules as in base 10. Just remember that you're working in a different base. That's all there is to it. And actually, the hardest thing involving different bases is conversion. That's the last thing I'm going to talk about. But if you were just strictly working with a particular base, you wouldn't even have to know how to convert. But it's nice since, if we decided for whatever reason to think like a computer and work in binary, which we're doing here, you might want to know how to convert this binary number to decimal 1001 1011. How do we do that? Well, the easiest way to do that, I don't know if it's the easiest, but the most straightforward, the one that kind of makes the most sense, just remember what this binary number means. Each number, each bit has to be multiplied by a power of 2 corresponding to what place it's in. And since there's 8, what, 1, 2, 3, 4, 5, 6, 7, yeah, there's 8 places here. The place on the left is the corresponding power of 2 is 7. So you start with the rightmost is just your units, that's 2 to the 0. So you should think of this number 10011011. All that means is it's 1 times 2 to the 7th, which is 128. That's the black line that gets bent and put on the bottom. I guess it's easier to start on the right. Let's start on the right. So it's easiest to start with the rightmost bit, which is a 1. So 1 times 2 to the 0 gives you 1. And then you have a 1 for the next place. That's 1 times 2 to the 1. That's 2. You don't worry about the third one because that's 0. You don't have to add anything here. Fourth one is another 1. So you have 1 times 2 cubed now. That gives you 8. Fourth one is 1 times 2 to the 4th. That gives you 16. And then you got a couple more zeros. You don't have to worry about those. But then the last one is 1 times 2 to the 7th, which is 128. And when you add up all these numbers, you got 155. That's how you do that's kind of the poor man's method for doing a binary to decimal conversion. There's easier ways to do it, but this kind of makes the most sense, I think. If you want to be a little more clever, you can do it different ways. There's another kind of trick you can use. So here's another way to do it. This is a different number actually, but here we have the binary number 10101101. And I think there's two different ways you can do this. There's like a top down and bottom up, but here they're doing the top down. So you start with the most significant digit, which is the one on the left. That's a 1. So you start with 1, and then your next digit is a 0. So you're doubling. I mean, you think about building this number up from the top down. You start with a 1, and then you add the next bit, which is a 0. That gives you 1 0. Well, 1 0 is just twice of 1. So your next step is to double the number you had before. Well, 1 times 2 is 2. And then you're adding 0 because that was your next bit. And then the next step, since the third bit from the left is a 1, this time you double again, but you have to add 1 when you're done. So you at the last step we added 2. So you have to double that and then add 1. 2 times 2 is 4 plus 1 is 5. And then you keep going like this. The next bit was a 0, so you just double 5. That gives you 10. Fifth step, you double again, but now since your fifth bit is a 1, you add a 1. That gives you 21, or 21. We're working on decimal now, so we can use the usual decimal names. 21. And then the next bit is a 1 again, so we multiply double again and add 1. That gives you 43. Next bit's a 0, and this time you just double. That gives you 86. Last bit's a 1, you double 1 last time and add 1. Gives you 173. Voila. So that's another way. I think that's a lot easier than the method I showed you earlier. You don't have to use powers of 2. You just double and add. There's a and then yeah. So and then going from decimal to binary. I think this is even easier, actually. And there's two methods. There's what's called a top-down and a bottom-up algorithm. This algorithm, I believe, is the top-down algorithm. So suppose you wanted to convert 156 as a decimal number to binary. How would you do that? Well, here's how you do it. First, you divide it by 2, and you see what the remainder is. And actually, I think this is the bottom-up algorithm. I'm not sure. I got them confused. Yeah, this is the bottom up. So this is going to give you the bits from right to left. So when you divide 156 by 2 and take the quotient, you have to do both the quotient and the remainder. So you write down the quotient below, that's 78. But then the remainder is 0. And what that means is that the last binary digit of your result is going to be 0. That kind of makes sense because 156 is even, right? Every even number written in binary ends in 0 because the unit's position is going to be a 0. So your last bit of the answer is going to be 0. And then you do the same thing with 78. 78, once again, is even. So your remainder is going to be 0, but you still have to do the quotient, which is 39. This time 39 is odd. So your remainder is going to be a 1. That means your third bit from the right is going to be a 1. And then you do the division again, you get 19. Again, that's odd, so your next bit's a 1 again. And then when you divide 19 by 2, you get 9. 9's odd again, so you have a third 1. And then you divide by 2, that gives you 4. This time this is even. So that's going to give me a remainder of 0. And then you divide 4 by 2, you get 2. That's even again, so you write a 0. And then the last number is 1, and you write a 1, and you're done. So if you wanted to write this 156 in binary, you have to go from the bottom up. It would be 100111100. That's the bottom up algorithm for converting from decimal to binary. But there's also a top down algorithm. I reversed these slides. I actually meant to do it in the other order. So this is kind of the hard way, which I showed you before. Yeah, bottom up is easier. For top down, you have to use powers of 2. This is harder because you first have to write down what all the powers of 2 are up to the number you're trying to convert. In this case, that's up to 128. So you subtract 128 from 156. That's the largest power of 2 that doesn't exceed 156. That's a 1. And the first bit of any binary number is always going to be a 1, by the way. Just like the first digit of any decimal number is never a 0. The first digit of any number in any base is never a 0. And since there's only two bits, two numbers in base digits in base 2, you know that every binary number in base 2 has to start with a 1. But we still had to know the power, and then we subtract that. And then, we just do the subtraction. We do 156 minus 20, 128. That gives you 28. And then the largest, so that means that the 64 place and the 32 place are both 0. Then 16 is less than 28, so we have to subtract 16 from 28. That gives us a 1 in the fourth bit, the fourth place. And then 28 minus 16 is 12. You subtract 8 from 12, that gives you a 1. So your next is a 1, your best is a 1. And then um, 12 minus 8 is going to be 4. 4 is the next power of 2 we're working with. That's going to give us a 1, but now 4 minus 4 is 0. We're left with nothing. That means that all the remaining bits are 0. So that's another way you can get the binary representation of 156. Notice that this is the same number, 100111100. It's the same number we had here. If you just read these bits from bottom to top. So those are two different algorithms for computing the decimal representation of a binary number. Nice. Okay, and then now I want to talk about, this is actually something easier. And this is important. If you were, suppose you didn't care about decimal. Suppose you just wanted to convert from binary to octal. Well, octal is a nice base because octal eight is a power of two. Eight is just two cubed. And what that means is it's very easy to go from binary to octal, and even the other way around, as I'll show you in a minute. So all you have to do is you have to notice that each of these numbers 0 through 7, each octal digit has a binary representation with 3 bits. Remember that every octal digit corresponds to exactly three binary digits, 3 bits. And here's the code. 0 is 000, 1 is 001. This is how you would count in binary up to 7. So you just get all these values in binary for each octal digit. And now all you have to do, if you want to convert a number from octal or from binary to octal, let's say this was your number in binary, 001, 100, 110. First thing you want to do is group everything. I mean, it would really be 1100110 because nobody writes zeros at the beginning. But suppose that was your number you want to convert to octal. Well, the first thing you have to do is you have to add 2 bits to the left because you always have to have a multiple of 3 if you're working an octal. And then you just group everything. So you look at the groups of 3. 001 in binary is 1 in octal. So your first group gives you a 1. That's your first octal digit. Your second group, 100, is 4 in octal. Is this table in binary? Is this table? Yeah, 100 in binary is 4 in octal. These columns probably should be reversed, but yeah. So 100 gives you a 4, and then the last group, 110, that corresponds to 6 in octal. So your answer is going to be 146. Voila. And it's just as easy to go in the other direction. So binary octal, I guess we were doing octal to binary. We were actually doing, I don't know, we were doing the other way around. So yeah, we were doing octal, binary to octal. So here's another example of binary octal. 110, that's 6. That's your first octal digit. 101 is 5. It's your second octal digit. So 100101 becomes 65 an octal. But it's just easy to go the other way. You just use the code the other way. 5, 6 an octal, since 5 is 101 in binary, that's your first 3 bits of the number. And then since 6 is 110, those are your last 3 bits. So 5, 6 an octal is 101110 in binary. And then let's look at the last example. 11111110. That's 7 bits. But remember, we always have to have a multiple of 3, so we have to add 2 zeros to the left. And if you did that and you grouped everything the way I showed, you would get 176, an octal. Here they do a different example on the bottom, going from octal to binary. I don't want to do a different example. But again, it's just the same thing in reverse. 6 is 110 in binary, 4 is 100, 3 is 011. When you put all those together, you get 110100 in binary. So that's how you do it. Pretty easy. And the same thing with hexadecimal. Hex, they usually call it. Hexadecimal, they shorten the name to hex, but hex is, I think hex is even used more than octal in computer science. Hex is kind of the basis for ASCII code. I'll get to that in a minute. But, same thing. I'm not going to go through this in detail, but you use the same kind of code. 16 is 2 to the 4th power, just like 8 was 2 cubed. So now you have to write a code for every hex digit. There's 16 of them, and now each of those codes in binary involves 4 bits. You just write them all down. You do the same thing. So an example they give here is 11100011. One, I mean, I'm going to say all the digits, but you group them all into 4s, and then I don't know. I must have chopped off some of the slide, but 0001 is just 1 in hex. 1100, that's 12. That's going to be C. So you get 1C. 0111 is 7. So that's going to give you 7. And then your 1011, that's 13. That's, I don't know, 11. That's going to be B. So you're going to get 1C7B. I should have chopped that part off. Here's some examples. So I'm not going to go through these, but it's the same idea. Just use your code. Remember that you have to change numbers 10 through 15 to A through F. So, if, for instance, I'll just go through the thing on the bottom here. If you're converting the hex number A9 to binary, you would use the code for A, which is 1010, and 9 is 1001. So your example is going to be 10101001. Anyway, that's how you do that. So it's pretty easy to go to and from uh, binary to octal and binary to hexadecimal. And this is done a lot in computer science. Here's a table. I don't know if you can see this whole table, but this table on the numbers on the left are decimal numbers from 0 to 15, and then they write them in binary. That's just 4 bits, and then they write them in octal. That's just 2 octal digits. And then if you write them in hexadecimal, you just get each hex digit. I guess they have 16 on the bottom. So 16 in hex is 10, but all the numbers 0 through 15 are just one hex digit. Um, and this is useful. This is very, very useful because it turns out that the ASCII code, the code for all the characters that are used on your computer, those are letters or symbols. Every symbol that your computer uses is an example of what's called a, a byte. A byte is 8 bits, and so we can represent. That's why computer scientists like to talk about bytes and kilobytes and megabytes and gigabytes and terabytes. A byte is 8 bits, and a byte represents a character. So when you say that a file has a megabyte, what you're really saying is it has a million characters, roughly. Uh, so a typical book will maybe have about a million characters. So a book is about a megabyte. Just remember that. That's a pretty good mnemonic. Your favorite book has about a megabyte of information in it. And these are just the ASCII symbols for, the binary hex and octal code of every ASCII character. This is how computers store their information, by the way. Every spot in computer memory has one of these representations of a character in it. Good thing to know. And also a good thing to know if you're interested in hacking code. That's why a lot of people like C, by the way, because C has a thing called pointers where you can actually access the thing in every position in the computer's memory. It's good if you want to kind of hack into what's going on in the computer hardware. That's why C is a very popular language. I think it's my favorite computer language, C and C++. Pointers are hard. I'm not going to talk about pointers anymore, but they're hard, but they're very useful because they kind of get to the nuts and bolts of what's going down inside your computer. I think Java doesn't involve any pointers, and I think part of the reason for that, Java, you're not really supposed to know what's going on inside your computer. You're just supposed to be able to work with I mean, they have a thing called encapsulation. I shouldn't go into this. I'm getting off track, but I prefer C and C++ for the reasons I just said. But anyway, so now the last thing I want to talk about, I think I've gone over how to do arithmetic in different bases in pretty much detail. The last thing I want to mention is these are some very popular alternate bases to base 10. I don't really like base 10. The only reason we use base 10 is because we have 10 fingers. And base 10 isn't really that good a base. I mean, think about it. 10 is 2 times 5. I mean, the reason I think so many people like base 12 more than base 10 is because 12 has more factors. 10 only has it has 4 factors altogether if you include one in itself. It has 2 non-trivial factors, 2 and 5. 12 has 4 non-trivial factors, 2, 3, 4, and 6. And what that means is that it's a lot easier to do arithmetic in base 12 and duodecimal, if you like, because more things divide into 12 evenly than in 10. That's why you get a lot of irregular, decimal representations of fractions in base 10. You know, 3 is already a repeating decimal, and so is 7. I guess that's still a problem in base 12, but at least in base 12, you can divide evenly by 3 and by 4 and by 6 and by a lot of other things. You can't divide evenly by 5 or by 7. A lot of people prefer base 6. I actually watched a very good video about a year ago about base 6. And the guy who made the video, he made a very, very good case for why he liked base 6 better than base 12. I mean, it turns out, I don't know. I mean, 7. If you look at the decimal representation of 1/7, or duodecimal representation of 1/7 in base 12, it's still pretty ugly. But it's not so ugly in base 6. I think it's just 0, 5 repeating. So maybe base 6 is better than base 12. The guy who made this video really seemed convinced that base 6 was the best base in the world, even though people have been pushing base 12 ever since I was a kid. But another base I like is the one on the bottom here. The Babylonians, actually. This is called sexagesimal, base 60. And the Babylonians, they used this about 3,000 years ago. They had these big cuneiform tablets where they did all their math and cuneiform. They had these wedge symbols. And they actually notice that they use two symbols for every at least every sexagesimal digit after 10. So they used like it was kind of a compound base system because they used wedges to represent all numbers from up to 9, just like we do in decimal. They just had different symbols for them involving wedges. But then they had another set of wedge symbols for the second digit, but they only went up to 5 for the second digit. So that allowed them to write every number from 1 to 59 is a set of two wedge symbols. And then if they wanted to write a bigger number than 60, they just had more than one set of wedge symbols. So they were basically using base 60. The only mistake they made was they did not have a symbol for 0. 0 was not discovered until the first people we know who ever used a 0 were the Mayans. The Mayans who lived in Central America. They were a primitive society that didn't survive, unfortunately. They were around from around I think around 1 AD, around the time of Jesus, to around 900 AD, and then the society died, unfortunately. They're the same Mayans who came up with a calendar that ends in the year 2012. And that's why so many people thought the year 2012 was going to be the end of the world, which I thought was really stupid because even the Mayans didn't believe it was the end of the world. It was just the end of their calendar. Unfortunately, their civilization ended before their calendar ended. But they were the first people we know that used a symbol for 0. They had a symbol that looked like a shell for 0. But the Babylonians, they were very, very good mathematicians. They were, enlightened enough to realize that base 60 was a nice system to work with, but they didn't have a symbol for 0, which meant that they got confused sometimes about their own numbers because there was no placeholder for 0. So they would kind of confuse, say, 101, which would have been 3601 in sexagesimal. They would think that some of them would think that was a 1 because they didn't have a 0. So they'd think it was 61. So they would get things like 61 and 3601 confused, which was a problem. But they were very, very good mathematicians. As a matter of fact, they came up with a very precise estimate of the square root of 2. They came up with a sexagesimal representation of the square root of 2 that was accurate, I think, to something like 10 decimal places. And this was around 1000 BC. Pretty amazing they were able to do that, I think. So they were very, very good mathematicians. And I guess base 60 worked pretty well for them. And one last thing I want to say about that, our time system. The fact that we use hours, minutes, and seconds. We have 60 seconds to a minute, 60 minutes to an hour. That came from the Babylonians. The Babylonians were the first people who used that convention. So our system of hours, minutes, and seconds is a relic of the Babylonian sexagesimal system. Pretty amazing. So base 60 I like. But base 6 and 12, I don't know which. These are my three favorite. I don't know which is my favorite. I haven't figured that out yet. But I think these are all better than base 10. And I think someday in the future, I think humanity will be using one of these bases. Probably not until, the 22nd century. I think the rest of the 21st century, we're still all going to be using decimal. I'd like to see America go metric first. It's going to take us long enough to sort out, how to do metric, which is based on base 10. That's probably going to take America through the end of the 21st century once we do finally adopt metric. And then by the 22nd century, if all goes well, maybe the world will decide to convert to one of these other three bases. Of course, none of us are going to be around then, or at least I'm not. Maybe some of you young kids will be, but I'm not going to be here in the 22nd century, unfortunately. I wish I could. Maybe in my next life I will. But anyway, that's my talk, and that's my talk on arithmetic and different bases. Thank you for watching. Long live math, and I'll see you next time.